Okay, good morning. Before going on with the new topic, I just would like to summarize briefly what we have done up to now, considering the different models that we have used to describe the band structure of the electrons within the solid. Um, Up to now, we have considered different models after seeing the indications that are given by the Bloch's theorem, that are indications concerning the shape of the structure of the wave function that we obtain in presence of a periodic potential. So the idea is that now the electron is moving in a potential such that the potential is invariant under translations made using vectors belonging to the Bravais lattice. The fact that there is a solution to the Schrödinger equation where we include this value of u of r means that the electrons is able to interact with the lattice, but this kind of interaction with the lattice is not the source of the collisions that were predicted by the Drude model and also by the Sommerfeld model. So this is an indication of the fact that actually the electron is not going to collide with the ions belonging to the lattice. Nevertheless, we have to include a collision mechanism in the model, otherwise the conductivity due to the fact that the wave function is stable should be infinite in this situation. So we have to include the presence of a scattering mechanism, but at the moment we don't know what is the physical mechanism behind this, behind the collisions. Then the different situations we observed were u of r equal to 0, so we reduce to the free electron picture. And in this case, the modification that is given by the application of a Bloch theorem is the fact that we have to introduce a periodicity of the energy. So this is a direct consequence of the Bloch theorem due to the fact that the wave function has the same symmetry. So n of k plus g is equal to nk. So this fact produces a modification in the band structure of the solid, even in the free electron approximation. Then what we observed is that a situation more close to the real condition of a material may be the situation where u of r is not 0, but can be considered as a perturbation of the free electron picture. So this is just a perturbation of the free electron model. What we observe here is that we have gap opening. So there is a distortion of the electronic band structure within the solid, and this distortion is observed where the in the free electron case we have a degeneracy. So we have a single value of the wave vector where we have at least two different values for the predicted energy. So in that condition, what we observe is that the degeneracy is removed by the presence of this small perturbation. So we have a gap opening, and the gap opening has as an effect the fact that in the free electron picture, one could start from the lowest energy level and continuously reach all the possible levels for the electron in the system. But when we have the gap opening, this is not possible. So it's not possible to move, to change continuously the energy of the electron, so to access all the possible levels. So due to the fact that this is not possible, the idea is that the different bands that build up the electronic band structure in the system are now disconnected. So due to the gap opening, again, the different electronic bands are disconnected due to the presence of this perturbation. And another thing that is the conclusion of the, not of the block theorem, but of the fact that we, in this new problem, let's say, we have a translational invariance, but this translational invariance is not as in the case of the free electron picture. So the system is not invariant under any arbitrary translation, but is invariant just under translations made by using vectors of the Bravais lattice. So due to this fact, we have that the, let's say, in the free electron case, the momentum of the electron was equal to h bar k. So in that case, from the wave vector, it was possible to evaluate the velocity of the electron. In this case, the velocity of the electron is given by 1 divided by h bar gradient of the energy with respect to the wave vector. So in this case, the, let's say, h bar k has not the meaning of momentum in the free electron sense. But due to the fact that it will have, in fact, and we will see that shortly, a meaning that is close to the meaning of momentum, h bar k is not called momentum as in the free electron picture, but is called crystal momentum. So this is crystal momentum. To distinguish that from, say, the momentum P, so we have again the need to, we may still use K as an index to distinguish the different electronic levels. And in this case, we do not need just one index, but we need both, at least two of them. One is K and the other one is N. So two indexes. We have seen that K is an index, is a wave vector that runs within the first Brillouin zone, and N is an integer, and N allows us to distinguish the different bands of the electronic structure. So in this picture, also the definition of the velocity is different from the free electron case. Then we consider two other situations. One is the case where U of R is strong and is close to the atomic case. And this is the tight binding model, where we use the opposite approach. So in the first part, we moved from U of R equal to 0 to U of R different from 0. So the actual description of the solid was a perturbation of the free electron case. Differently, in the tight binding model, we start from the atomic picture and we consider the solid state picture to be just a perturbation of the atomic one. So we use the opposite approach. We try to describe an electron that is able to move within the solid, but this electron feels the strong effect of the ionic potential. So in this case, the interaction with the lattice cannot be considered just a perturbation, as that interaction has a strong effect on the electronic levels. So in this case, we were able to build up a combination of, let's say, atomic wave functions. And in that combination, we also include the presence of a phase of the wave vector, so to have the opportunity to see the, let's say, to detect the capability of the electron to move through the solid. And that capability was related to the so-called superposition integral that was labeled by gamma. And gamma was an integral where we had electronic wave functions, atomic electronic wave functions, and the presence of the perturbation, where in this case, the perturbation delta U of R is equal to the atomic potential minus the solid state potential. So in this case, again, the perturbation is the appearance of the solid potential with respect to the atomic one. So in the regime where U of R was small, we considered something electronic levels that were close to plane waves. When the U of R is strong, then we consider electronic wave functions that are close to the atomic ones. Then there was a sort of summary between these two approaches that was the orthogonalized plane wave method, where we try to combine plane waves So in this case, we combine plane waves and tight binding wave functions, or in general, wave functions that display a strong effect of the atomic potential. So to build up a new electronic wave functions where we are able to combine the, let's say, free electron behavior that the electron is expected to display when the electron is not in strong, let's say, when the distance between the electron and the ion is not so small, and the, let's say, tight binding behavior that the electron is expected to display when the effect of the ionic potential is strong. So this approach combines the two pictures, and thanks to this approach, it's also possible to, let's say, introduce the concept of pseudopotential, where pseudopotential is a combination of the actual ionic potential, so the effect of the lattice, plus the potential due to the interaction between the, let's say, plane wave component of the electronic wave function and the core electronic wave function. So this is a sort of interaction between the plane wave part of the wave function and the electrons that are strongly bound to the ion. Thanks to this definition, so thanks to the definition of the pseudopotential, we see that the actual potential that the free electron feels when that free electron moves in the solid is a combination of the ionic contribution of the potential, so the Coulombian interaction with the ions, plus the electron, let's say, electron contribution that is due to the, again, the interaction between this plane wave part of the wave function and the core electron wave functions. And while this is negative, because interaction is the interaction of a negative charge of the electron and the positive charge on the ion, this is positive because at the end is the interaction between electrons, so same charge particles. So the actual contribution of this pseudopotential is to reduce the strength of the pure ionic potential. So in this picture, we may suppose that the fact that some metals actually behave as, let's say, nearly free electron metals can be justified by the fact that for those metals, the contribution of the interaction with between the plane wave part of the electron and the core electrons is strong enough to, let's say, nearly cancel the ionic potential, so to let the, let's say, plane wave part of the wave function feels just a small average potential within the solid. So this is a justification of the fact that in some cases, this picture works fine. Because when I told you that U of R could be considered to be just a perturbation of the free electron case, I didn't give you any justification, any physical motivation behind that approximation. But when we study the effect of the pseudopotential, then we know that in some cases, that approximation can be fine. And actually, when you go to the lab, you observe that in some cases, for some metals, the free electron picture is actually the nice, good picture to describe the properties of those metals. So at the end of this part, what we may see is that irrespective of the method we want to use to describe the electronic properties, we are able to evaluate an expression for the energy dependence as a function of K and as a function of N. So what I'm supposing now is that using one of these models or an additional model that can be used to evaluate E of N as a function of K, we know that dependence. So from now on, I will suppose that this dependence is known, because the next step will be to try to describe what is the dynamics of the electron in the solid, considering the presence not of free electrons as in the Sommerfeld picture, but of block electrons. So from now on, we will suppose to consider just block electrons in presence of E, H, or electromagnetic waves. So we will try to do the same thing that we did with the Drude case in an extended mode, or with the Sommerfeld case, and try to see what is the mutual contribution of, let's say, external fields effect, E, H, or electromagnetic waves, and lattice effect. Because the block electron, when we consider the problem of block electrons feel the effect of at least two groups of forces. One group of forces is the group that is the, let's say, classical one. So the effect of the electric field, magnetic field, electromagnetic waves. On the other side, we have internal forces, that is that are due to the interaction between the other electrons and the ions that build up the solid. So the next step will be to, may I switch to another page? Okay. So the next step is to study the effect of, again, external fields, so electric fields, magnetic fields, electromagnetic waves on the electron dynamics. That is more or less what we did to evaluate the, for instance, the conduction in the Drude model, or the magnetoresistance or the resistivity in the Drude picture, and also in the Sommerfeld one. So this is the idea of the topic. This will be the topic of the next lessons. Then, just to summarize what we have done up to now, because that will be useful to understand how we may proceed using just block electrons, we may just briefly review the main equations that were used for, just to start with the first model in the Drude case. In the Drude case, we just use pure classical equations. And if you want to solve a problem, let's say in classical dynamics, you consider the fact that the derivative of the position vector is equal to the velocity, and then we have that and then we have the second law of dynamics, where the acceleration of the particle is is equal to the external force, and we may just rewrite this as the derivative of momentum with respect to time. So this was just the Drude picture. When we move to the Sommerfeld, case, in this view, Sommerfeld uses classical equations. Sorry, So yeah, Sommerfeld uses classical equations, but tries to describe the electron not in a classical way, but using a quantum mechanical approach. In this new approach, if we want just to rewrite these equations considering the new approach, the velocity can be written as p divided by m. So in this case, we have the derivative of the position vector is equal to momentum, and momentum in the Sommerfeld case is the momentum of a free electron. So it's h bar k divided by m. Then we have, if we look at the second law of dynamics, we have the derivative of momentum is equal to f. In the Sommerfeld picture, momentum is h bar k. So if we just write the same things, we have the derivative of momentum, that in this case is h bar times the derivative of k with respect to t, is equal to f, where f is always the, let's say, Lorentz force given by electric and magnetic fields. In the Sommerfeld case, the electron is not is described by plane waves, not by, let's say, the classical point particle that moves in space due to the external fields. So even if the single electron wave function is a plane wave, if we look at the probability density to find one electron in the system that is given by the, let's say, plane wave, that probability density is constant over the space. So this means that the electron is not localized everywhere. You have the same probability to find the electron in any place of the solid, the same probability to find the electron in any place of the solid. So to try to use this representation, to try to build up a representation of the electron as a sort of, not a point particle, but something that is more localized than the plane wave, what we used was the combination of plane waves to build up a sort of, let's say, propagating wave within the system. And in general, if you remember electromagnetic waves, in that case, so you have that the equation for one wave is given in this way. Then to build up a sort of combination of plane waves, so to have a localized structure that propagates through the solid, we may use a wave function so that the value of k is not just one. We have a combination of k values, but the combination is just that that combination of plane waves give up a sort of, let's say, Gaussian profile or a Lorentzian profile. So if we make a sort of snapshot of the electron at the same value of the time, then we have that the position. So if this is the square modulus of the wave function, so the square modulus of the wave function, I just finished. Okay, so sorry, I just changed the symbol, so not to have the same symbol. So if I call this psi of RT, and here I represent the square modulus of this psi of RT, then that modulus is not, let's say, uniform over space, but is different from zero in a region of space. And what is omega? In general, omega is related to the energy, because we know that the relationship between energy and frequency is given by h bar. So in this case, as we let's say consider free electrons, and the free electron energy is given by the usual quadratic relationship between k and energy, we may rewrite omega as E divided by h bar, where E is the free electron value. So in this case, it's possible to build up a wave function that has a propagation in space and time, and that wave function describes an electron. This describes an electron that is, let's say, not localized, is not just a point particle as in classical mechanics, but at least can be localized in space. If we switch to the block electron picture, so for block electrons, at this point, if we want to use the same approach for what concerns the description of the electron, in this case, we may again make reference to a combination of waves. In this case, if you remember the block electron wave function has a phase times, is made by a phase times a sort of modulation of the phase. So if you look at this expression, in this expression we have, if you just consider the space dependence of the wave function, we have this phase e to the I k r. The same phase is found here. So at this point, we may just consider a combination of block wave functions where we just need to consider the block wave function, not just the plane wave as we did for the Sommerfeld case, due to the fact that the plane wave that we have here is included in the block wave function. We just need to include the time dependence. So just to write that more clearly, this part here is energy as a function of k divided by h bar times t. So in this case, we have something that is similar to the Sommerfeld situation. We do not write explicitly the phase because the phase is included in the block wave function. If we want to let the phase to be directly present in this summation, we may just rewrite that as sum of g of k. I write the expansion of psi, where we have u and k of r, and then we have the so we have at this point the phase that gives us the indication concerning the space dependence, and also the second part that is an indication concerning the time dependence of the wave function. If we want to, let's say, use the same approach as before, so to use this combination to describe an electron that is more or less localized in space, we want also to fulfill another requirement. In principle, g of k is not a delta, is not a Dirac delta. So if you use g of k as a way to combine different electronic wave functions in this combination, g of k will be centered around the given value. I call that value k0, but will not be again a Dirac delta function. So we'll have a spread. If that function has a spread, that means that that spread means a combination of different wave functions that correspond to different values of the wave vector. What is the consequence of that? If the spread of that function is wide or is large with respect to the size of the first Brillouin zone, this means that when you describe an electron using the band diagram, you may not just describe that electron using K0. I just make a plot so that to make it more clear. So if I suppose that for instance, yeah, I just make the plot for the nearly free electron picture because it's easy to plot that here. So if we use this picture just to have a diagram to discuss, what we have done up to now was to, let's say, access all the levels just by choosing the value of K. So before I use K0, for instance, if K0 is here, I may directly access, for instance, this level here, because that level is indexed by that value of the wave vector. If in place of using K0, now I use G of K, where G of K is a function like this, a weight function like this, that is centered at K0, but has a width that is not 0. This means that when I say K0, I do not refer just to one level. I refer to many levels that are close to K0. So if the width, if I call delta K the width of that function, if delta K is smaller and smaller with respect to the size of the first Brillouin zone, so if this condition is fulfilled, then I may say that K0 so if delta K is small with respect to the size of the first Brillouin zone, when I say K0, I'm not referring to a single level, but I'm referring to a group of levels that are very, very close to K0. Due to that, I may, let's say, making a sort of approximation, consider the sentence, the electron is described by a combination of different wave functions that are close to K0 as a sort of synonym of the electron has a wave vector that is K0. So I may use the old way of saying that was a single wave vector refers to just one electron, even if in this case the distribution is not a Dirac delta, but has a width that is different from 0. I see some question marks on your faces, so I'll try to repeat that in Italian. Yeah, if you don't mind, I try to repeat this in Italian, then I go on in English. Il punto è questo: se introduciamo una funzione peso che costruisce una funzione d'onda localizzata a scapito del fatto che però bisogna usare più valori di k per fare questa combinazione, non c'è più una corrispondenza biunivoca fra elettrone e valore di k, perché un elettrone corrisponde a più valori di k. Quindi a questo punto perdo la corrispondenza biunivoca fra valori di k ed elettroni, perché non c'è più. Quando è che posso far finta di recuperare questa corrispondenza biunivoca? Quando delta K è piccolo. perché se delta K è piccolo, posso ancora continuare a pensare che individuare un singolo K voglia dire individuare un singolo elettrone, perché di nuovo delta K è piccola, quindi non mi accorgo della larghezza della distribuzione quando guardo lo schema a bande. Se viceversa uso una funzione peso g di k che è molto larga nello spazio dei k, allora vuol dire che quando dico K0, adesso esagerando, se avessi una g di k molto ampia, invece di dire K0 solo 1, è come se dicessi K0 K0 è tutta quella fascia, è tutto quel range di K. A quel punto ho perso completamente la corrispondenza biunivoca livello, scusate, ho perso completamente la corrispondenza biunivoca elettrone singolo K, perché se le cose fossero così diventa impossibile dimenticarsi del fatto che l'elettrone è descritto da un'autofunzione che è una combinazione di molti valori di K. Quindi diciamo che l'idea di base è, se voglio continuare a usare uno schema a bande, qualsiasi esso sia, mantenendo questa corrispondenza biunivoca fra elettrone e vettore d'onda, in quanto il vettore d'onda mi fornisce da numero quantico per definire, per accedere, per identificare i vari elettroni, devo fare in modo di utilizzare delle funzioni g di k che non siano delle delte di Dirac, ma non abbiano nemmeno un'estensione molto grande. Per questo l'idea è cercare di avere delle G di K, ok, ampie, ma con una larghezza più piccola della zona di Brillouin, perché alla fine l'elettrone lo gestiremo come conseguenza del teorema di Bloch, sempre usando vettori d'onda della prima zona, quindi l'importante è riuscire ancora a mantenere questo legame 1 a 1 fra indice K e elettrone che stiamo considerando. Quindi da ora in avanti, pur avendo in mente il fatto che l'elettrone non è descritto da una singola onda di Bloch, ma da una combinazione, io darò sempre per scontato che quella combinazione sia molto stretta e che quindi possiamo far finta di dimenticarci del fatto che appunto esista questa funzione peso g di k, ma possiamo continuare a ragionare come se di nuovo ci fosse una corrispondenza 1 a 1 fra elettrone e valore del vettore d'onda. Vi torna? È un po'... Anche chi segue il collegamento, questo passaggio torna?
Sì.
Ok.
Adesso torno, grazie.
Okay, so at this point, in principle, the best solution could be, let's say, to use the same method that we used up to now. So again, a Dirac delta, so something with a width that is very small. But the problem is that if in the wave vector space you use a combination that is very narrow, when you go to the Dirac space, the Fourier transform of g of k is not a narrow function, but is a function that is very wide. So the problem is that if delta k is too small, so if delta k is too small, then delta of r, where delta of r is the uncertainty concerning the position of the electron in the Dirac space, that so if delta k is at the limit equal to 0, then delta r becomes infinite in the real space. So we have to, let's say, try to find the balance between localizing the electron in the reciprocal space, because otherwise we lose the localization in the real space. So if delta K is smaller and smaller with respect to, let's say, 2 pi over A as an estimate of the size of the first Brillouin zone in the case of the cubic lattice, then since the width of the electron in the direct space is more or less inversely proportional to the, let's say, width of the electron in the reciprocal space, and this is just due to the Fourier transform process. So if you make a Fourier transform of a function that is very narrow in one space, you have on the other space a Gaussian, let's say, function that is very wide. So you have to balance the width of the two distributions, and due to that, let's say, due to the requirement that we have here, they should be larger and larger than A divided by 2 pi, where A is the lattice spacing. At this point, A, again, is of the order of some angstroms. So if we accept that let's say, localization, our capability to localize the electron in the direct space is not on the angstrom level, but is on the nanometer level, then we may, let's say, lose some knowledge on the position of the electron because we don't know where the electron is on the scale of the ions, but we just know where the electron is on the scale of nanometers. But if we accept that, then we are able to use the Venn diagram and the, let's say, a good localization of the electron in the wave vector space. So we are able again to use the one-to-one correspondence between wave vectors and electronic levels. And is this a problem? So is this is it a problem to know the position of the electron, for instance, over the let's say an uncertainty of 10 nanometers over the electron position? Is it a problem or not? Let's say the answer to this question is not one. So it's not just one question. We have many questions, many answers, sorry, depending on what is our objective. So if our idea is to investigate what happens when we use static fields, then that's not a problem, because even if the width of the electron is 10 nanometers, the field has exactly the same value over, let's say, all the size of the electron. If we use not static fields, uniform fields, but if we use electromagnetic waves, if we do something similar to what we did with the Drude model, so visible waves, in the case of visible light, the wavelength of the electromagnetic waves is of the order of, let's say, 400, 700 nanometers. So this means that even if the uncertainty over the position of the electron is 10 nanometers, due to the size of this wavelength, that is not a problem, because 10 nanometers is very, very small with respect to 400 or 700 nanometers. So again, we may consider that the field over the electron as a fixed value. We do not need to consider the dependence of the field over the size of the electron. So due to the fact that the idea is to try to, let's say, apply all the methods and all the aims that we had in the Drude case also to the block electrons, so to investigate conductivity, magnetoresistance, optical properties, that means properties in the visible range, then this uncertainty is not actually a problem. So we may keep the one-to-one correspondence between electrons and wave vectors. We may, let's say, miss the capability to localize the electron in the direct space with an uncertainty that is of the order of the lattice spacing, but this is not something we have to fear, because we may use, let's say, we may do all the calculations or our tasks considering that the electron also in the direct space is a sort of point particle, because with a wavelength of the order of 400 nanometers, we do not need to localize the electron over the lattice, over the scale that is of the order of the lattice spacing. So a problem would be if the size of the electron was 100 nanometers, but with 10 nanometers, we are fine. So also in this, so from now on, I will suppose that for the aim of localization, both in the direct space and in the reciprocal space, the electron will be described by this G of K, this distribution of wave vectors. But this distribution is chosen so that we do not miss the, let's say, point particle picture, both in the reciprocal space and in the direct space. Okay. At this point, what's time? Yeah. At this point, we just need to, if we rewrite the equation of motion that we use in the Sommerfeld case, at this point, the equation of motion, we have the one concerning the position vector. The position vector is the derivative of the position vector is equal to velocity. And for Bloch electrons, we know that velocity is 1 divided by h bar, the derivative of k of En of k. So we just change the representation of the velocity, considering what is the expectation value of the velocity for Bloch electron. Then if we just rewrite the second law of dynamics, then we have the Lorentz force, the classical expression for the Lorentz force applied to the electron. I make just a comment on that, and then I make the break because we have past 10 o'clock. The general idea is to use exactly these equations for the description of the dynamics of the electron. But what is an important point that has to be considered for these equations? The first equation is just a rewriting of the corresponding equation in the Sommerfeld case and Drude case, considering the new expression for the velocity. If in general you consider the second law of dynamics, who is F? F is the total force. So you have to sum up all the forces and then discuss on what happens to the acceleration. But in this case, the total forces are, let's say, the classical forces, so what is found within the Lorentz force or what is due to electromagnetic waves, plus what can be called as microscopic forces, so the effect of the interaction with the ions and the electrons. An important point is, what is the scale of those forces? The scale means what is the variation in space due to that is induced by, sorry, what is the variation in space that corresponds to those forces? If we consider the classical forces are due to uniform fields. So in that case, the typical scale is infinite because we have that the force is uniform over space. If we consider electromagnetic waves, in that case, we consider visible light. Visible light has a wavelength of hundreds of nanometers. So over the, let's say, size of the electron, those forces, the intensity of those forces is nearly constant, because the variation over space of those forces is larger and larger with respect to the size of one electron. If we consider microscopic forces have a range of variation that is of the order of the lattice spacing. So the range of variation of microscopic forces, I just write 3 angstroms, not because that is the exact value of the range of variation of the forces, but because that is an average value for lattice spacing. So that is just an estimate of a size, is not a precise value for what concerns the range of variation. So what is a consequence of that? If we consider, besides the, let's say, size of the electron, also the de Broglie wavelength of the electron. The de Broglie an estimate of the de Broglie wavelength of the electron can be obtained just considering an electron whose wave vector is equal to kf, just to find an order of magnitude. So if we use kf to estimate the de Broglie wavelength of the electron, we saw that for as kf depend to the electronic density, we saw that if n is of the order of 10 to the 28 electrons per cubic meter, then kf is of the order of 6 times 10 to the 9 meters to the minus 1. So lambda is 2 pi over kf. At this point, if, let's say, we suppose that 2 pi is nearly 6, just to make an approximation, then this is of the order of 1 nanometer. So this means that the de Broglie wavelength of the electron is larger than the range over which the microscopic forces show a variation. So this means that if we want to write down the second law of dynamics, we may not consider in the same way classical forces and microscopic forces, because classical forces have a range of variation that is larger and larger with respect to even the de Broglie wavelength of the electron, but microscopic forces do not have the same feature. So at this point, we have a problem, because we may not write down the second law of dynamics, including all the forces. So we may not use a purely classical picture, because we have to consider also forces that are quantum mechanical in nature. But the idea is also to not use a fully quantum mechanical description of the problem. So what is generally done is to use an approach that is in between the two. And due to that, this approach is called semi-classical, where semi-classical means the external forces, the effect of the external forces is described using two equations of motion that are nearly equal to the classical ones. And in this case, if you notice, the role of momentum is ascribed to what we call the crystal momentum. So in these equations, what was the role of momentum in classical mechanics is the role that is a role that now is given to crystal momentum. So in this case here, we do not have the actual momentum, but we have just crystal momentum. So the external forces affect the value of the crystal momentum, and then what is the effect of that? If you change the value of the crystal momentum, you change the value of the velocity, but the velocity is handled through the energy, and the energy is quantum mechanical in origin. So the effect of the quantum mechanical forces, for instance, the forces due to the interaction with the lattice, is handled through the energy, because the energy is the solution of the Schrödinger problem where we had the interaction with the electrons or ions or whatever. So E of E, the energy expression, the energy band structure is due to the, let's say, microscopic forces. So the effect of those forces is just included in E. The effect of classical forces is handled through the Lorentz force. So let's say the scheme is classical force changes the crystal momentum. If the crystal momentum changes, then the velocity changes, but this change of velocity is obtained not in a classical way, but in a quantum mechanical way, because that is handled through the energy, and that affects the position, and so on. So we have two levels of approximation for what concerns the effect of the forces over the electron. The classical level that affects the crystal momentum, not the full momentum, just the crystal one, and the quantum mechanical forces that appear in the equation through the energy. So the effect of the lattice of the electronic band structure is just through E, and again, the effect of the classical forces is just observed through the variation of the crystal momentum. Due to this double level of approximation, this picture is called semi-classical because it's not fully classical, but is not quantum mechanical either. So we have an approach that is in between the two. So it's more easy to handle since the external forces are handled classically. But you know to, let's say, have already solved the Schrödinger problem. So you need to know the solution of the Schrödinger problem because you need to know what is the energy band structure of the electron you are going to investigate. And so in this, from now on, we will make reference to this picture for the solution, to try to solve the equation of motion to see what happens to the electron. That is not a free electron, but is a block, just a block electron. So what I will try to do after the break is to solve those equations using E, H, a combination of E and H. Okay,